Where does the glare come? In the monitor? Oh, on you. Directly on you. Is that okay? Is the recording okay? Will the recording be okay? Fine. So the first item is we wish all of you a happy new year, and the second item is we want to talk about the three basic components: resistance, inductance and capacitance, energy considerations in them. Then we want to talk about sources, current and voltage, and we want to work out a couple of problems. Then if time permits, we wish to enunciate two circuit laws. This would be the scope of today's lecture. Most of this material is known to you, and therefore what we are doing essentially is a review of the knowledge that you already have. A resistance, as you know, is defined by a linear resistance is defined by Ohm's law, that is the potential difference across its terminals is proportional to the current that flows in it, V and I, and the value is R. Experimental law is that V, the voltage drop, is proportional to I. The more current goes, the more is the drop, and therefore the proportionality constant is given the name resistance, and it is denoted by R. Now if it is a linear resistance, then if you plot V versus I, note the polarity. Polarity is V is considered positive in this direction, that is from where the current is originating, V is considered positive, and the current going to the other terminal, that terminal is considered negative. And the relation between V and I naturally then shall be only in the first quadrant, and it shall be a straight line whose slope is equal to R. Now if this relationship becomes non-linear, then we say the resistance is non-linear. Most of the times we shall be concerned with linear resistances. In linear resistances, the power, that is the energy consumed per unit time, dW dt, is given by the product Vi, and therefore this is P equals to I squared R, and the energy that is dissipated in the resistance in time capital T shall be equal to I squared R T if I is a constant, if the current is a constant, if I is constant. If I is not constant, then the relation shall be R T integral I squared dt from 0 to capital T. This would be the general form. Is that okay? The general form would be the integral of R I squared dt, no T, I am sorry, R I squared dt integral from 0 to capital T. If the current is a constant, then it will be simply I squared R times capital T. This energy is dissipated in the resistor, that is, the dissipation means a transformation of electrical energy to heat energy, all right, and this is an irrecoverable process, irreversible process. That is, if a resistance dissipates heat, dissipates energy, this energy cannot be recovered, all right. On the other, therefore in a resistance the energy is dissipated and not stored. On the other hand, in an inductor, for example, well, first let us take a capacitor. Let us consider two parallel plates like this, two parallel plates which are separated by a distance d, and let us connect a battery of voltage V. There are two plates, parallel plates like this, all right, separated by a distance capital T. They are parallel to each other, and we connect a battery across this. Then you know that the upper plate shall be charged positively and the lower plate shall be charged negatively. Now if I disconnect the battery, the charges remain, all right, and therefore this device is capable of storing electrical charge. The charge does not disappear as soon as the battery is disconnected. Therefore it acts as a storage of charge, and it is found that the charge stored in the device is proportional to the potential difference V that is applied. That is, if you increase the battery voltage to twice its previous value, then the charge doubles, and therefore Q is proportional to V, and the proportionality constant is given the name of capacitance. This is the capacitance for storing electrical charge, and is given the symbol C. Now naturally, if it is a linear capacitor, then the relationship between Q and V is a straight line with a slope of C, and this is called a linear capacitor. Not all capacitors are linear. For example, there are devices called varactor diodes in which the capacitance varies as the square of the voltage, and therefore there the capacitance is non-linear. The charge is not linearly related to the voltage. If it is linearly related, then we say it is a linear capacitor. It is not a current voltage relationship. This is what I want to point out. The linearity does not exist between current and voltage. It is between charge and voltage. This is the basis of linearity. Now if Q is a constant, then naturally if V is a constant, then Q is a constant, all right, and therefore no current flows. If there is a battery here, the battery will not deliver any current. I shall be equal to 0 if capital V is a constant. On the other hand, if V varies, all right, then obviously Q also varies. If V varies, then Q varies, and if Q varies, then there shall be a flow of current which is proportional to the rate of change of charge. In other words, if the charge in a capacitor varies, then the current flowing through this shall be given by I equal to C, I equal to dQ dt, which would be equal to C dV dt. Let us use a small symbol, small v. I equal to C dV dt, and therefore the current voltage relationship is no longer linear. What is linear is the current and dV dt relationship. That is, if I plot current versus dV dt, not V mind you, then this relationship shall be linear, exactly like the charge is linearly related to the voltage, all right. And the usual the symbol for a capacitance is this, that is two lines parallel to each other, and the value of the capacitance is written by its side. Similarly, for what about the energy? The power, again in this case, is given by VI. Power is the product of voltage and current, and since I is C dV dt, therefore power is C V dV dt, all right. And therefore if we charge a capacitor from 0 to a voltage, let us say capital V, if we charge a capacitor from 0 voltage to a voltage V, P is equal to C V dV dt. If we charge a capacitor from 0 to a voltage V, then the energy that is stored in the capacitor shall be given by integral P dt, from V equal to 0 to V equal to capital V, and this therefore is equal to C integral 0 to capital V V dV. dt and dt cancel, the rate of change with respect to time, and therefore the energy stored in the capacitor is half CV squared. Why is it stored and not dissipated like in a resistor? Because this energy can be extracted, can be recovered from the capacitor. If you leave the capacitor after charging to a voltage capital V, if you leave it intact, if you do not disturb it, it shall maintain its charge for time immemorial, time ad infinitum, all right. and therefore this energy can be recovered. For example, if you take a capacitor, charge it to a voltage capital V, then you short circuit the two terminals, that is the two terminals you connect by means of a zero resistance wire, then a spark passes and the wire gets heated, and therefore this energy can be recovered from the capacitor, and therefore this energy is a stored energy. Now how does it store energy? If there are two plates which are plus V and 0, then you know the lines of force start from the positively charged plate and go towards the negatively charged plate. This is the direction of the lines of force. What is the direction of the electric field? Same as that of the lines of force, and therefore if I put a positive charge here, this positive charge shall go towards the lowest potential, that is zero potential. Alright. The point that I was mentioning is that this energy is therefore stored in the electric field that exists between the two plates. As I said, if there exists a charge or a set of charges, then an electric field is said to be created, because another charge brought into this field feels a force of repulsion or attraction, and therefore there is a field of force, and this field of force is called the electric field. Therefore in a capacitor the energy is stored in the electric field. On the other hand, if I take an inductor physical manifestation is that of a coil. If you take a zero resistance wire and wind it, let's say around this pen, then it becomes a coil and it behaves as an inductor. The property is that if a current passes through it, I, then a magnetic flux is generated around this coil, and the flux, experimentally it has been found that more the current, the more the magnetic flux, and therefore phi is proportional to I, the flux is proportional to I, and the proportionality constant is I. Linearity of an inductor implies that if I plot phi versus I, it is a straight line with a slope of capital L. If it is not linear, if the relationship is not linear, then we say the inductor is non-linear. For example, an iron core inductor, as you know, if you increase the current sufficiently, the core tends to get saturated, and that's why you get all those hysteresis phenomena and all that. Whenever saturation occurs, it is a display of non-linearity. The flux current relationship no longer remains linear. Here also, if the current remains constant, then the flux remains constant. On the other hand, if current varies, then the flux varies, phi varies, and then a voltage is generated across the inductor, and this voltage is given by d phi dt, and this is equal to L di dt. Our convention would be that if this is the inductor and the voltage, the potential difference is V, the current is I, then V is equal to L di dt. This would be our convention. Whenever we draw a circuit element called an inductor, this will be the sense of polarities that we shall adopt. Now an inductor stores energy. It also stores energy, but not in the electric field now, it is in the magnetic field, because an inductor is associated with moving charges. Unless a current flows, it cannot generate a flux, and therefore the energy is stored in the magnetic field, and this stored energy can now be utilized for example for inducing voltage in a nearby inductor. Alright, energy can be transferred from one inductor to another. If you place a nearby inductor in the magnetic field of force, then the second coil develops an EMF across it. Alright, so energy can be transferred, and here also if you write the power expression, it is VI, and which is equal to I L di dt, L di dt, and therefore the energy that is stored in the magnetic field is given by integral 0 to t in time capital T. If the inductance is L, then I di, I beg your pardon, 0 to capital I, because T cancels out, and this is, what did I do? I made a mistake, I di, okay, dt cancels because W, dW is equal to P dt, and therefore dt and dt cancel, and therefore what I get is half L I squared, half L capital I squared. Therefore an amount of energy half Li squared is stored in an inductor in the magnetic field, and in that sense a capacitor and an inductor, they are both energy storage elements, and they are called dynamic elements, dynamic, whereas a resistance which does not store energy, which only dissipates energy, is called a static element. All right, a circuit which contains only resistors can be described by an algebraic equation. A circuit which contains only resistors can be described by algebraic equations, whereas a circuit which contains at least one energy storage element, either an inductor or a capacitor, at least one, you cannot describe the circuit by means of an algebraic relationship. You have to use a differential relationship, and wherever differentiation with respect to time is involved, the system or the circuit becomes dynamic because its property changes with time. All right, so capacitance and inductance are dynamic elements, and a resistance is a static element. You must understand, I repeat, what we mean by a linear resistor, a linear capacitor, or linear inductor. A linear inductor does not mean that the voltage current relationship is linear, isn't that right? A linear inductor means the flux current relationship is linear. All right, a linear capacitor means that the charge voltage relationship, QV relationship, is linear. A linear resistor means VI relationship is linear. This must be kept in mind. Now, as you know, energy under any circumstances cannot change instantaneously. Whether it is a mechanical system or an electrical system, the total energy cannot change instantaneously. For changing the total energy of a system, you do require a certain non-zero amount of time, because if energy can change instantaneously, by definition dW dt, which is the power, becomes infinite, and infinite power can neither be achieved nor can be conceived of, and therefore one of the fundamental relationships is that if you fix any time, let us say t1, then the energy at time t1 plus must be equal to the energy at time t1 minus. In other words, just before t1, whatever the energy is must be the same as the energy just after t1, and therefore if that is so, then you remember that energy in a capacitor is half CV squared, and therefore since energy cannot change instantaneously, the voltage across a capacitor cannot change instantaneously either. Isn't that right? In other words, Vc, in general it shall be true that Vc 0 minus would be equal to Vc 0 plus, where Vc is the voltage across a capacitor. In a similar manner, energy in an inductor, which is given by half Li squared, since W cannot change instantaneously, therefore IL, current in an inductor, at 0 minus must be equal to IL 0 plus. I must point out that this 0 is an arbitrarily fixed reference. It could be T1, it could be T2, or whatever it is. We have taken this as 0 as the point of reference. These two principles, that the energy, that the voltage across a capacitor cannot change instantaneously, and that the current in an inductor cannot change instantaneously, will be extremely useful in analysis of circuits, electronic circuits or otherwise. After introducing these three elements and their energy relationship, let us look at some active elements, active circuit elements. The three elements R, L and C are called passive because they cannot generate energy. A resistance can only dissipate energy, it cannot store, it cannot generate. An inductor, in order that it stores magnetic energy, it stores energy in the magnetic field, it must be fed with a current. It cannot generate on its own. In a similar manner, a capacitor cannot generate energy. Any device which cannot generate energy, it can either dissipate or store, is called a passive device. On the other hand, an active device is one which can generate energy. A battery, for example, is an active device. A rotary converter or an electromagnetic generator, a rotating electrical machine which generates electrical energy, is a generator. Now, there are two kinds of active circuit elements that we shall basically be concerned with, and these are voltage sources or current sources. Voltage sources and current sources. Now note these definitions carefully. A voltage source is a generator which maintains its terminal voltage constant irrespective of what you connect across its terminals. That is, even if the load is changing, if the load changes, then what changes is the current, but the voltage across the terminals remains V plus irrespective of what the load is, and therefore this is called a voltage source, or sometimes the adjective ideal is appended to it, ideal. For an ideal voltage source, naturally, if I plot V versus I, the terminal voltage versus current, it remains a constant like this. In an actual source, however, in an actual battery, for example, or in an actual electromagnetic wave generator, the voltage usually falls as the load current is increased. In an ordinary power supply, as you shall see in the laboratory, if you take more current, then the terminal voltage decreases, and this non-idealness can be accounted for by introducing a small resistance here, and this resistance is called the internal resistance of the source. A non-ideal voltage source shall be modeled as an ideal voltage source V in series with a resistance R, and therefore if you plot the terminal voltage, now let us call it Vt. If you plot the terminal voltage Vt versus I, then what will happen? The curve shall no longer remain parallel, but it shall droop, because Vt, as you can see, is V minus I R, and therefore it is an equation to a straight line, but it slopes, it decreases as I increases, and at any point if this is the current, then this difference is I times R. Is that clear? The difference between an ideal voltage source and a non-ideal voltage source. Is this clear?
So this line always a straight line.
Will this line always be a straight line? Yes, if this resistance is linear, then this line shall always be a straight line. If you have a linear resistance, because what you get is this, the terminal relationship is given by Vt equal to V minus IR, which is an equation to a straight line, provided small r is a linear resistance, that is, it does not depend on either the current or the voltage. Alright, situation is slightly uncomfortable if we consider a current generator I, capital I, it maintains a constant current irrespective of what the load is. If the load changes, then what changes is the voltage V, not the current. The current capital I remains the same. That is, a current generator maintains its output current the same irrespective of what load you connect. So, if we plot I in the load versus V, then V changes but I does not change. Alright. In a practical current source, now you must follow this carefully. In a practical current source, usually the current drops as you increase the load resistance. Usually the current drops like this, and this can be modeled, this drop can be modeled by introducing a parallel resistance like this here, small r. Under this condition, you see the current in the load, the green color I am using for non-idealness. The current in the load shall be given by capital I minus what? Small v divided by small r, which is a linear relationship, and therefore as V increases, this term increases, and therefore the current I decreases. Now, if I had drawn, we shall have such such games in the tutorial class. If I had drawn it the other way around, suppose we draw V here and I here, what kind of a characteristic I would have got? For an ideal source, it would be a vertical line. For a non-ideal source, tilted towards, is it this way?
Yes.
Okay, that's wonderful. We will have all such orientations in the tutorial class, and we shall consider consider tricky problems where it's slightly it takes a bit of time to figure out what kind of shape the current voltage characteristics are. Two particular cases of termination shall be important. Termination, that is, you have let's say an active element. It's either a current source or a voltage source. It could be ideal or non-ideal. I'm representing this by means of a box with two terminals. All right. Now, two particular cases of termination are extremely important in electrical engineering and in electronics. That is, if there is no termination at all, that is, the load resistance is infinite, then this condition is known as the open circuit, OC. Open circuit means the circuit is opened and therefore no current can flow. All right. Pardon me? Can I repeat that part? One of the conditions of the load, one extreme condition is that the load is infinity. Load is infinity means no resistance is connected across the two terminals. If no resistance is connected, then the circuit is open and therefore no current can flow, and therefore this is called the open circuit condition, open circuit. On the other hand, you could also have a situation in which no voltage can drop across the terminals. That is, you connect them by a zero resistance wire. That is, RL is equal to 0. If RL equal to 0, then whatever current flows through RL, it cannot drop a voltage, and therefore V, the terminal voltage, is equal to 0. And this condition, well, open circuit is the condition for I equal to 0, and short circuit is the condition for V equal to 0. This is called a short circuited condition. Short circuit is usually accompanied by a spark because of the large amount of current that can flow, virtually zero resistance. And if this is an ideal voltage source, if this active element is an ideal voltage source, then how much current can flow? Infinite amount of current, which also points out to the fallacy of conceptualizing an ideal voltage source. An ideal voltage source naturally cannot exist. If it can exist, then it should be capable of delivering infinite amount of power, which is not possible. Agreed? And therefore an ideal voltage source is a conceptualization only. It helps in analyzing electrical and electronic circuits, and therefore a bit of an ideal voltage source or similarly an ideal current source cannot be realized in the laboratory. What would happen if you get an ideal current source? You can generate almost infinite voltage, isn't that right? An ideal current source, if it passes through an infinite resistance, which is an open circuit. You see the fallacy? Open circuit means current cannot flow. But on the other hand, if the source is ideal, then obviously the total current should pass through an infinite resistance, and the voltage should be infinity. Therefore the power that it is capable of delivering shall be infinity, and therefore it is also a hypothetical element only. So well, I have also introduced incidentally the concept of terminals, which is very easy to see that if you have a circuit, if you have an electrical circuit which has only two terminals available, then it is simply called a two-terminal circuit. Okay. It is also called a one port. Well, the concept of a port is exactly like that of a ship docking at a port. Well, since this is an electrical circuit, an electrical ocean, what you can dock in is either a voltage source or a current source or a load. So what all that can be done is to connect from here to here. You can connect a voltage source or a current source or a resistance. So this is called one port. It has only one port. Suppose you have a circuit in which there are three terminals like this. Well, actually both of these are the same, three terminals like this. Then you can dock in two sources, all right, and therefore this is called a three-terminal network, three-terminal circuit, or a two-port. If a circuit has more than two ports, it's called a multi-port. All right, you can have a three-port circuit. The number of terminals shall depend on whether there are any common terminals or not. For example, in this circuit, this terminal 3, let's say, is common between port 1 and port 2. You could have a two-port which has exactly 4 terminals like this. This is a two-port. All right. You can also have a two-port which has 3 terminals in which these two are connected, and usually they are connected to ground. All right. Now enough of concepts. Let's work out a couple of examples. The first example that you take is that of a fuse. You know what is a fuse? It's used in domestic power supply. There is a fuse which blows up if the current exceeds a certain limit. All right. A fuse is a non-linear resistor. When the current goes high, the voltage drop across it is such, or the heat generated is such, that it blasts, it blows off. So it disconnects the electricity and saves all the equipment in the house from being damaged, from passing high current. A fuse, it melts when the current becomes excessive. The resistance, it is given that the resistance of a fuse is given by R equal to RR 1 plus C times T. All right. It is given that the resistance of a fuse is a function of temperature. Capital T is the temperature rise above the room temperature. That is, capital T is actual temperature minus room temperature. Okay, capital T is the difference between the actual temperature and the room temperature, or it is the rise above the room temperature. C is a constant, proportionality constant, and R sub R is the resistance of the fuse at room temperature. All right. It is also given that the temperature rise above the room temperature is proportional to the power that is being fed to the fuse. That is, capital T, the rise above room temperature, is equal to some constant K times P. What is wanted is determine an expression for R in terms of the current I and evaluate the current I such that the fuse blows off. This is the problem. All right, you understand what we mean? A fuse can be sufficiently accurately modeled by a relationship like this, where the resistance is given by the resistance at the room temperature multiplied by 1 plus a constant times the rise of temperature of the fuse above the room temperature. And this rise is understandably proportional to the power supplied. That is, more power is supplied, the more will be the heat generated, the higher would be the rise of temperature. The question is to find out R as a function of I and to find out the current I at which the fuse blows off. Now you can see that capital R is equal to RR 1 plus C K P. Capital T is Kp and P is I squared R, and therefore capital R, if I take this term to the left hand side, becomes equal to RR divided by 1 minus C K I squared R R. Agreed? This is therefore the expression. Now what is the relationship between R and I? Is it linear? No, it is a nonlinear relationship. So capital R, you see, a linear resistor should not depend on the current at all. A linear resistor should not depend on the current that flows. Therefore it clearly shows that the fuse is a nonlinear resistor. Number 2, at what current does it blow off? Now when it blows off, capital R becomes infinity. Blows off means what? It becomes open circuit, and therefore capital R becomes infinity. Capital R equal to infinity when this denominator term becomes equal to 0, and therefore capital I becomes equal to 1 over square root of C K R R. That is the solution to the problem. Is that clear? Very simple problem. Any question on this? No. Let's take another problem. This problem is the connection of a resistance and a capacitance in parallel. You know what is parallel connection and what is series connection. In a parallel connection, the potential difference across the elements are the same. In a series connection, the current in the elements are the same. Okay? This is a parallel connection C and R, and this circuit is used to smooth out the fluctuations in a current I. All right. If I is not a constant, let's say I is something like this. I is a constant on which is superimposed a small sinusoidal AC. Then this circuit smooths out these irregularities. In other words, the voltage V will approximately be a constant. The voltage shall not display the ripples in the current, and therefore this voltage shall be approximately constant, and let this constant voltage be equal to capital V. All right. In that sense, this circuit is said to be a filter. It is as if it filters out the small ripples in the current. All right. Now for good filtering, it is said that the capacitance should be able to store, WC should be able to store 10 times as much energy. WC, the criterion is that the energy stored in the capacitor should be 10 times the energy dissipated in the resistance R during one cycle. That is, during if you take this sinusoidal, then this is one cycle, this is capital T. Alright, during one cycle of the ripple, the energy dissipated in the resistance, 10 times that should be the energy stored in the capacitor. This is the criterion that is specified. It is also specified that capital R is 10K. Capital R is 10K. You know what is a K? K is 10 to the power 3. Kilo is 10 to the 3. So 10K is 10 to the 4 ohms. R is 10K, and these ripples are at 60 cycles per second. 60 cycles per second. That is, in 1 second there occurs 60 such cycles. Alright. What you are required to do is to find out capital C. Alright. Now the solution, do you understand the problem? Is the problem clear? Okay. The solution to the problem lies in writing a relationship for WC and energy dissipated in the resistance. WC is half C V squared. Alright. This we have already derived. This should be 10 times the energy dissipated in resistance. What is the energy dissipated in the resistance? I squared R, but I squared is V squared divided by R squared times R times T, capital T. Now what is capital T? Capital T is 1 over F. Alright, so 1 over F. F is the frequency, okay, cycles per second. So it would be 1 over 60, and therefore I get C as equal to 20. Alright, V square and V square cancel. C is 20, R and R square, 20 divided by R times 60. Put down the value of R. This is 20 divided by 10K is 10 to the 4 times 60, and the unit shall be farads, okay, after the name of Michael Faraday. Alright, and this you can calculate this as 33.33, okay, microfarad. That's it. These are two advanced problems given in the book, and you can see that they are not quite difficult as long as you understand what the problem is. And it is extremely important that you understand the problem, because it is said that once you understand the problem, half of the problem is solved. The other half is simply calculation. I would like to conclude this class with a discussion on the two words which I have intentionally not used so far. Network. We said that our course is Introduction to Electronic Circuits. Alright, and we have always said circuit element. Circuit elements could be passive or active, and we have said energy, maybe energy shall be dissipated in a resistor, energy shall be stored in an inductor or a capacitor, energy can be generated in an active device, and so on. However, as you shall see as we go through the course in the textbook as also in my lectures, I shall almost use these two words, circuit and network, interchangeably, almost interchangeably, but there is a difference between the two terms. A circuit necessarily provides for at least one closed path for the flow of current. A circuit necessarily should provide a path for flow of current. So there, and a path means a closed path. That is, if a current originates somewhere, let's say in the battery, then there is a resistance, it cannot be left like this. There must be a closed path for a current to flow. The current, if it is open circuit, the current shall not flow, and therefore a circuit necessarily has at least one closed path. Now this path could be a short circuit or could be through another resistance. All right. So a circuit necessarily shall have at least one closed path. On the other hand, a network is a more general term. A network is a more general term. A network may contain circuits or may not contain circuits. For example, if you have a tree like this, well, this is a network. You say it is a network of branches, leaves, but it does not contain a circuit. That is, if a chemical starts rising up like this, well, it cannot come back to the tree unless you provide another path like this, which happens in the big banyan trees, for example. You have those adventitious roots, and therefore the chemical, the juices flow in a circuit. The point that I am mentioning is a network is not necessarily a circuit. A network may not contain a circuit at all. A network is a more general term than a circuit. And when you enunciate theorems, for example, we will use the term network theorems because they are applicable to more general situations. All right. Whereas when you say about laws, we say circuit laws. KVL, Kirchhoff's voltage law, and KCL, Kirchhoff's current law, they are both circuit laws, because in a network there is no significance of these laws. These laws apply to closed paths. Is that correct? Closed paths. What about KCL? KCL applies at a node. The total current entering must be equal to the total current leaving. But there is a presumption that there exists a current, one or more currents, and therefore there must be a circuit. Right? And therefore the KVL and KCL are circuit laws. On the other hand, when you enunciate theorems which apply to circuits as well as non-circuits or a combination of them, we say network theorems. And we shall study circuit laws and network theorems in tomorrow's lecture. Okay.